Continuing our revisitation of the theory of hypothesis tests, this was the curve that represented the distribution of sample means. Our population mean was here in the middle, or some sort of fixed value, and our distances were going to be measured in units of standard error. So this is all according to question number 7. In question 5 and 6, that was a bit different. This was observations, and distances were in deviations. But now we're talking about sample means and standard errors. In the last video, we had talked about critical values, and really even before getting into that, we needed an approach that would allow us to determine whether or not the population mean could be 211, given that we observed a sample of 167. So our approach here was to say, well, if a sample is close to 211, then we will accept the idea, we will fail to reject, that the long-term mean, that the population mean, is in fact 211. So we'll go with the idea that it's 211, and if our sample is close to that, then cool, we'll stick with it. But if our sample is not close to 211, then we are going to reject that idea, saying it's too unlikely to have seen what we saw given this assumption, so this assumption is probably not true. That led us to have to define, well, how close does close need to be? And so we do this using a probability. We're going to say that close will be if our sample, if there's a, for instance, a 90% chance of seeing what we saw, given that this is true, then we will assume this is true, or at least we'll go with it. And if there is a less than 10% chance, so 1 minus that 90%, if there's a small chance of seeing this, assuming this is true, then we will assume that is not true. So that 90%, oftentimes it is 95%, but you can really set that to be whatever you want. That value is called the confidence level. So we want to be 90 or 95 or 99% sure in our results. So we take that same number and say, well, if it is 90 or 95 or 99% likely to see what we saw, given this, then okay. Conversely, that means the complement of that, which we call the significance level, says that if there's only a 10% likelihood of seeing what we saw, then we're going to say it is too unlikely. That 10% comes from 1 minus 0.9. If we had a confidence level of 95%, then we say, well, if there's only a 5% chance of seeing this, then we will reject that. And so that significance level refers to the amount of area, the probability on each side, the total area on the curve. So we're talking about a two-tailed hypothesis test here, because we just care whether or not our value equals 211, which means it could be less, it could be greater. We're not going to differentiate. So since question 7 is using a confidence level of 0.9, that means our significance level, the complement, is 0.1. And so we'll take that 0.1, we'll divide it in half, and we'll stick 5% over here, and we'll stick 5% over here. That is the foundation of hypothesis tests. So this and this are our rejection regions. And if our sample mean is kind of falling in here, then we will reject the null hypothesis. So that's where this idea of critical values comes from. So again, this is just a review from last time. So there's our region that defines 90%, a 90% chance of the mean being close to 211, close to the population mean. So this threshold and this threshold identifies how many standard errors away a result needs to be. And a result for us is a sample mean. So how many standard errors away a sample mean needs to be before it falls in a rejection region. And I think I had identified that this was going to be 2.3, and since the curve is symmetrical, that is minus 2.3. That should be a 3. So the critical value tells us how many standard errors away our sample mean needs to be before it falls in the rejection region. So that's, I guess, half the deal. It tells us the threshold, but then we have to know how far away our sample mean is. And we do that using the t-score. So the t-score converts our actual mean, 167, into a number of standard error units. And that's what we do. The t-score, I think I said it was like -5. So here's the minus side. -5 is going to be over there. Take minus 5.5. So that is our t-score. The t-score was much more extreme. It's very far into this rejection region. So we would reject the null hypothesis. So that is one way, and a perfectly always applicable way of determining whether or not to reject or to fail to reject the null hypothesis. Is the t-score, or the z-score in the case of a normal distribution, and is the t-score more extreme than the critical value? We have a similar method of doing things based on the p-value. So we started off by defining our confidence level, saying that if our data, if there's a 90% chance of seeing what we saw, then we will fail to reject the null hypothesis. And there's a 10% chance we will reject our null hypothesis. So that gives us kind of a probability of 5% here. So the p-value says, well, what is the probability of seeing what we saw under this assumption? And since we have this threshold of 5%, or 10% in total, if our probability is smaller than our significance level, 10% in this case, if the probability is smaller than that, then it is too unlikely to see what we have seen under the null hypothesis, so we will again reject our null hypothesis. Ultimately, we're kind of saying the same thing. So when we did the critical value, we did that by identifying an amount of probability on either side, our rejection region. And so our p-value is also doing the same kind of thing and saying if our probability is small enough that it would fit inside this rejection region, then we need to reject the null hypothesis also. We have a somewhat similar equation to do that. So the critical value, we were given, or we give Excel a probability, and we get a distance in standard error units. And a p-value, well, the p stands for probability, so we want to end up with a probability, so we have to give it a distance. We give it a t-score and a degrees of freedom, and it will give us a probability back. And so if that p-value, let's see if I can draw here, if that p-value is less than the significance level, so 0.1 in our case, then we are in the rejection region, and so we reject the null hypothesis. And conversely, and simply, if the p-value is greater than alpha, then we're somewhere still in this 90% things are okay region, and we fail to reject the null hypothesis.